So hi everyone. So till now, what we study already? Actually, I already study like that the construction of the depletion and enhancement type MOSFET, body effect, pinch of voltage, and many more things. Okay. In this video, I will discuss the short channel effect. But before the going that, okay. So firstly, this equation I already see. Okay, so this equation I already saw the current equation in case of the saturation region. ID is equal to Kn by 2 Vgs minus Vts ka whole square when it will be there Vgs greater than Vth and Vds greater than Vgs minus Vts. You know already, I hope. Okay, this is the thing I wrote here. Okay, so in the last video I told like that the current will be constant in case of the saturation region. Means so this graph I already explained. Means so this is the so like that. So this is the linear region up to that, and this is the saturation region. And I already explained like that in the previous video. So current will be the constant. So current will be constant in case of the saturation region. Okay, but practically this thing not happen in reality. Okay, because of the channel length modulation parameter. So because of the channel length modulation, so this constant in the saturation region current will be not saturated. Okay, so here I will discuss the channel length modulation. So due to the channel length modulation, the current will not constant in the saturation region. Okay, and so I think you should have an idea of the long channel effect, the long channel and the short channel. What are the meaning? The long channel and the short channel. Okay, long channel and the short channel is the short channel is also called the second order effect. The second order effect, it can also called. What are the meaning of that? The meaning is very simple. Suppose we have a I am considering here the NMOS is there. Okay, and here is the source, and this is the drain. So in case of the long channel, the distance between the source and drain is more compared to the short channel. Okay, like 180 nanometer technology. This is the technology parameter, and the 90 nanometer technology. But when we bring, so this is the drain terminal. Right now I'm writing just for understanding. So this is the drain terminal and this is the source terminal. So if we bring near to near the drain terminal to the source like that, so this is called the short channel. Okay, because of that, so we short the channel like that. We bring near to near the drain terminal. So this is the drain terminal. Okay, and right now the channel. So why we do that thing? So to gain, yeah, to increase the low power consumption. The low power so it should be the low power consumption. Okay, and the speed should be more, and speed should be more, and the area should be less, and area should be less. So there is a different advantage is there. Just three thing I'm telling here. The power should be low. The means power should be so power consumption should be low, speed is more, and area will be less. Okay, so that thing. So due to that, we bring near to near the drain terminal to the source terminal. Okay, so this is the short channel. Okay, short channel, yeah, second order effect you can tell. So first, the second order effect I will discuss in this video, that is the channel length modulation. Okay, so I already explained it occurs in case of the saturation region, and so channel length modulation it occurs into the saturation region. Okay, so here I consider the one NMOS. Okay, here I consider the one NMOS. Okay, and I already told I mean, and this is the so length of the channel. Okay, no, if I increase the VDS, suppose initially the VDS is the 0 volt. Okay, so the nothing happened on the drain side. But when we increase the VDS, like VDS apply be the VDS one. Okay, we increase the VDS. So I already told like that when we increase the VDS, so there is a internally diode is there between. So there is a internally diode is there between the body terminal and the drain, and source side is also there. But here I'm focusing right now Okay, this is the P terminal and this is the N terminal. So if we increase the VDS value, means the reverse bias, the voltage across the PN junction we are increasing. If reverse bias voltage we increase, then the penetration of the depletion layer will be start like that. The penetration of the depletion layer will be start like that. Okay, so this is the penetration of the depletion layer. Means suppose we have a challenge right now, so this is the penetration. If we, so in the cross section part here I'm doing for simplicity. So this is the drain terminal and this is the source terminal, and this is the our the complete channel is there. So this is the complete channel length is there. Okay, so now if we increase the VDS, so the penetration of the depletion layer will be occur at the drain side. Okay, this thing I explained. Okay, and so when we increase more and the more VDS, the penetration of the depletion layer will start like that. Penetration of start like that, and I told already. So when the VDS will the reach at, so will be reached at the VDS set. On that state, the current will be saturated. This is the VDS set. So this is the VDS set. So when we increase the VDS, and it will reach up to the VDS set, at that the current will be the saturated. Actually, so this thing I explained the previously, and we increase the further VDS compared to the VDS side, the current will be constant. That thing I explained the in later video, but this thing is not happen practically due to the channel length modulation. Okay, so if we increase the VDS, the further further VDS that the penetration of the depletion layer, means the channel length is depleted like that. In the in phrase figure I am telling. So suppose this is the our channel is there. Okay, so this is the channel is there. This side is the source terminal, and this side is the drain terminal. Okay, so the penetration of the channel is like that. So this is the VDS side, and if we increase the VDS compared to like that. Okay, so I am showing here. So this is the complete channel length. So this is the L. Okay, okay, and this channel length is depleted like that. Up to that the channel length is depleted. I am telling delta L. Okay, and this is the effective channel, the channel length. Okay, L minus delta L, L minus delta L. Okay, so in this region, there will be positive ion is there. No? Actually, in the channel, the electron is there. So no, the channel is just start to the depleted. So this is the depleted ion is there. The positive ion is there. Okay. I hope you understand. Okay. So the value of the L is the actual length. So this is the actual channel length is there. Okay. This is the actual the channel length. Okay. Actual channel length, and delta L is the depleted channel length. This is the depleted, so depleted length. You can also tell this is the depleted length. And L minus delta L is the effective channel length. Effective, this is the effective length. Okay, so this is the effective length. I hope you understand. Okay, now, so I will see what are the effect is there. Okay, uh, so the current equation into the saturation region is mu1 cox w bata L into 1 by 2. This is the L, and I will write in the very good manner. Actually, the equation of the equation of the current is, that is the ID mu n cox, so the w bata L into 1 bata 2. Okay, and VGS minus VTH का whole square. Okay, so this is the equation of the current in the saturation region. But if I tell like that, if ID is equal to mu1, now the channel length will be replaced mu1 cox w bata, so L will be, okay, L will be replaced as the L minus delta L. So because of this is the effective length now, because of that the delta L is the depleted length. Okay, so effective length is L minus, So this is the you can say this is the ID set. This is the ID set, saturation region current. But now, so due to the channel length modulation L minus delta L, it will be replaced. Okay, L minus delta L into 1 by 2 into VGS minus VTH का whole square. Okay, I hope you understand now. So if we take the common L, if we so if mu1 COX W, if I take common from L, then 1 minus delta L by, so delta L by L, okay, into 1 by 2 is there, 1 by 2 into VGS minus VTH का whole square. Now, so you know already one thing is like that. So if 1 minus x to the power minus 1 is there, so we can write like that 1 plus x. If x is a small, x is a small, then you can write like that. Okay, so now I am writing. So this is the mu1, so mu1 Cx, this is the W bata L into 1 by 2, this is the W by L, and here VGS minus VTH whole square, and it will go in the up. So if it will go up, then 1 minus delta L by L to the power minus 1. Okay, so I can write like so. Here I'm representing the so this is the mu1 COX and W by L into 1 by 2. Okay, and VGS minus VTH whole square. Okay, and if I write like 1 plus delta L by L. Okay, so by the help of this is a mathematical equation. With the help of them I write. Okay, now. So finally, due to the channel length modulation, I am writing kn by 2, because kn by 2 into VGS minus VTH whole square. Okay, and 1 plus delta L by L. Okay, that thing. But I will modify this to because see, actually, so this is the delta L. L is depend upon the VDS value. VDS will increase, the delta will be increase. Okay, so the delta will be directly function of the VDS minus VDS sat. Because of that, at the saturation region comes, if we increase the VDS, if we increase the VDS further, the further the VDS sat, the VDS sat, then the penetration of the depletion layer will start. Means that this is the depleted layer channel length. We can see observe. So this is the delta L. If so for the so for constant, I am introducing that is the lambda dice into VDS minus VDS sat. Okay, VDS minus VDS sat, and I am dividing both sides with the L. So by dividing L, this is the L. Okay, so delta L by L we can write like that, delta L by L, and lambda dash by lambda I am replacing this thing with the lambda. Okay, and if the VDS is more and more compared to the VDS sat, in this case the lambda and lambda into VDS. Okay, so delta L by L, because of that the depleted channel length delta L is the function of the VDS. When we increase the VDS, the depleted channel length will also increase it. So finally I am writing the equation here. Due to the channel length modulation, id is equal to kn I am writing. Okay, kn by 2. Okay, and vgs minus vth whole square, and 1 plus delta L by L you can write like that. What are the terminology? 1 plus lambda VDS. Okay, this is the additional term came. So due to the channel, now the current equation in case of the saturation region like that. Actually, previously we have up to that we have kn by 2. Kn you know already, no? Kn you know already, no? This is the mu1 COX and the W bata L. So kn by 2 VGS minus VDH whole square 1 plus lambda VD. So lambda is called the channel length parameter. Channel. So this is called the channel length. So this is called the channel length parameter. Okay, and what are the unit is there? The unit is lambda. So lambda unit is volt inverse. So how I am telling? Okay, how I am telling volt inverse. Okay, so because of that, so now we can observe like that. This is the in case of the saturation region, if we don't consider like that, If we don't consider the channel length, firstly it will give the linearly, and it will be constant like that. So no CLM means no channel length modulation is there then. But if we consider the channel length modulation, then it will go in that in the saturation region, the the current will be increases like that. Some amount of the current will increases. Why? Because of the delta L is the depleted channel length is increasing now. So due to that, if we throw in a slope, so this terminal it will cut like that. So this is the ID, this is the ID, and this voltage is so this is the early voltage is there. Okay, early voltage. Now I will define the early voltage. What are the meaning of the early voltage is there? And this is called the VDS. Okay, VDS. Okay, early voltage. So early voltage are those voltage at which the drain current will be zero. So up to this terminal you can write like that. So this is the zero into ID axis. Okay, and this is the this terminal is the point is minus VA or comma 0. Okay, so how can we calculate the how can I calculate the slope? The slope is equal to y2 minus y1 ID sat. This is the saturation region current. So this is the ID sat, y2 minus ID sat minus 0 divided by 0 minus VA, 0 minus of VA. So the slope is ID sat divided by VA. This is the slope. And one thing is also called so this is the complete the saturation equation is there. No? This equation we can also write like that. So this equation ID is equal to and this current equation. So this is the ID sat because this all are the saturation region current into 1 plus lambda into VDS. So you can observe this equation by a y barabar mx plus c. So mx plus c, ID plus constant, but the lambda VDS into ID set. So ID set into lambda is the slope value of m. So here I am replacing ID sat into lambda is equal to ID sat divided by VA. Okay, so lambda is equal to 1 bata VA. So this is the early voltage, and the unit of the lambda is 1 bata VA. You can observe like that. Or okay, so this is the channel length. So this is the channel length parameter. Channel length the parameter. Okay, channel length parameter. Lambda is equal to 1 by VA, and unit is the volt inverse. Okay, and about the early voltage, I already told the early voltage, the voltage at which the voltage at which the drain current will be zero. The voltage at which the drain current means id drain current id will be zero. So that is called the early voltage is there. I hope you understand like that. So this is the final equation in case of when we consider the channel length modulation parameter. Okay, means finally I am writing id is equal to kn by 2 VGS minus VTH whole square and 1 plus lambda into VDS. So in this video, I discussed the first short channel effect, a second order effect, that is the channel length modulation. Okay, and if you want to calculate the output resistance, if you want to write, then you can write output resistance in the saturation region. So no need, if you want to remember, then no problem. Output resistance in saturation region. If you go the DC analysis of the MOSFET, na, that time you need this expression. So here I am directly writing output resistance of MOSFET in saturation is so 1 bata the lambda into ID, 1 bata lambda into ID. ID is ID sat. Okay, this is the ID. You can calculate just so you can calculate. I'm telling the derivation. So just you need to so you need to consider this expression and the partially derivative with respect to VDS, and we will get this expression R naught barabar 1 bata lambda ID set. Okay, I hope you understand this first short channel effect, yes, second order effect, the channel length modulation. Okay, so if interviewer ask like that to explain the channel length modulation, then no need to explain all the equation. Okay, just you need to explain like that. Consider nmos, and when we increase the VDS, and what happened like that I explained already. And you need to make this figure, and this is the circumflex L is the channel length, and this is the depleted length and effective length. And you need to put this thing in the main equation, saturation region equation, and you need to derive like that finally, right? And finally you can replace also delta L by L is 1 plus lambda into VDS. Up to that is enough, up to that is enough. And after that he will ask anything interview, then you need to tell everything. Okay, otherwise the channel length modulation just you need to explain. Okay, this is the thing. And finally you should write this expression kn by 2, that is the mu n check w bata L guna 1 by 2 VGS minus VTH को whole square 1 plus lambda VDS. I think this is the enough. If you explain this way, he will definitely very happy. Okay, so in this video I will explain the first short channel effect. Yeah, yeah, second order effect, that is the channel length modulation. So thank you everyone. In the next video we will meet.